The last session we were seeing what do you mean by the commutation process, how there is a changeover of the current from one side to another side when they are come across the different poles. Once again recap the things, that is we know that the current which is induced in the armature conductor is alternating in the nature. These current will flow in one particular direction under N pole and they are changing its direction when they come under the influence of the other pole, that is S pole. This reversal of current takes place along the magnetic neutral axis, or it's also called as brush axis. That is the process by which current in the short circuited coil, which is reversed while it crosses the magnetic neutral axis, is called as the commutation. Then the changing over the current from the one particular direction to other particular direction, the total time taken for changing over the current from one direction to the other direction is called as a commutation period, that is represented by the TC. Okay. Now we are seeing all this process, how there is change in the current takes place when the coil is moving, whereas the brush is stationary. That is, if you are concentrating on the coil B, in which in this particular portion, when the brush come in contact with the commutated segment B, the current which has got a path of 20 amperes from the coil A and coil C are as follows. That is, even though there is a current path here, but as such there is no the exit path for from the commutated segment A. Therefore, this 20 amperes has to go through the coil B and is enter into the commutated segment P. Then it goes to the brush. Therefore, the current here is this 20 amperes will flow through the B as well as the C is collected by the commutated segment B. Then the total current is the 40 amperes. Then just you have to concentrate on the coil B, in which the current is in the clockwise direction. Okay, or it is from left to right. Then this coil and the commutated segment, they are moving continuously. Suppose if it is moved further in such a way that is the part of the brush is come in contact with the commutated segment A, because this coil is moving from left to right. Then now once again the current is remains same, which is collected from the coil A side is 20 amperes, from the C is 20. Then how there is a path here, that is now A has got some path here through the commutated segment A and also through the B. Then the total current path is as follows here, that is out of 20 amperes there is a 10 amperes will take a path through the commutated segment A and the brush, and the remaining 10 amperes has to flow through the coil B and it is collected by the commutated segment B. Then the total current is 40 amperes. Now we can see here, then when the commutated segment is moving, when the brushes start coming in contact with the A, the current in the coil B goes on the decreasing. Further, if the coil is moving, then what happens here, the half of the brush is in come in contact with the A and the B. In that case, the current which is from the A has to take the whole path through the commutated segment A, 20 amperes. Another 20 amperes from coil C has to take the path through the B, and the total current is the 40 amperes. Then you can observe here the current is 0. Means this coil B is now in the magnetical neutral axis. Therefore, there is no current is induced here. Therefore, here from 20 amperes to it is reduced to 10 amperes. When it is reached to magnetic neutral axis, the current is 0 now. Now, further the coil is moving, so that the majority of the portion of the brush is in contact with the commutated segment A. In that case, the 20 amperes is collected from A and the 20 amperes from C, out of which very small portion is in contact with the brush here. Therefore, only the 10 amperes is collected by the commutated segment B. The remaining 10 amperes will flow through the coil B. Just you have to observe the direction of the current. The previously it is in the clockwise direction, you can call clockwise direction. Now it is the change its direction. It is under the commutation. Therefore, from the clockwise to it is changed into anti-clockwise direction. Now the total current which is collected for the commutator segment A is 20 plus 10, that is total 30 amperes, and from B it is 10 amperes, the total amperes is the 40. The further the coil is moving so that the brush is totally in contact with the commutator segment A, then what happens here? That is, now here it has this 20 amperes as flowing here through the commutator segment A. That is, however, this 20 amperes it has to take the path through the B, because the whole commutator segment will come in contact with the brush. In that case, it has to, the B has to change from plus 28 to minus 20 amperes because of the sparking in the brush. Then what happens? The 5 amperes is passing directly from B to the brush in the form of the spark. Then the remaining 15 amperes will flow through the B, and the total current is now 40 amperes, 35 here and 5 in the form of the spark. Then the total current is 40 amperes. If the reversal will take place from plus 20 to minus 20, then it is called as ideal. Now it is not changed fully, therefore it is the under commutation. Thereby we are shown here the figure. Then what in by the ideal condition, that is plus 20 to minus 20. If it is less than 20 amperes, it is reversed. In that case it is called as the under commutation. It is under commutation. Same thing is drawn here, that is the ideal commutation and the under commutation. Then the time from change from one direction to other direction, then it is called as the time of commutation or commutation period, or it is also called as a commutation period. Okay, then how to improve this the commutation process, how to get the sparkless commutation? There are two methods they are adopting. One is called as resistance commutation, another one is EMF commutation. In the resistance commutation, what they are doing here is, this method of improving the commutation consists of replacing low resistance copper brushes by the comparatively high resistance carbon brushes. That is, you have to avoid that sparking by making the brush itself with very high resistance, so that it is made of carbon, so that it is offering very high resistance to the spark. Therefore, it has to take the path to the commutator segment. So that is a resistance commutation is nothing but replacing low resistance copper brushes by carbon brushes. Then the next method is the EMF commutation. Before discussing the EMF commutation, then what you mean by the reactance voltage we will define, then we will go for the EMF commutation. That is, we know that the changing of the current from one direction to other direction means it is changing. You have seen in the previous section that the current is from the 20 amperes in the positive direction, which goes on decreasing to 0. Then it is reverse, it is increasing in the reverse direction. Means there is a continuous change of the current in the coil as it is moving in the magnetic field. Therefore, if there is a change in the current in any coil or a conductor, it is possessing the inductance. That is, the property of the inductance is that it is opposing change of current in it. Because while commutation there is change in the current in the coil, that is, there is the existence of the inductance by which there is a voltage is inducing. That voltage is called as the reactance voltage. That reactance voltage is given by L di by dt. Then what is the di? That is change in the current. The change in the current is from plus IC to minus IC, or plus I to minus I, or you can take an example of 20 amperes to minus 2 amperes. Then what is the time taken for this? It is called as the commutation period. That is what we are calling as TC. Okay. Then how to find out this reactance voltage, that we will discuss. That is, in the actual practice, the current in short circuited coil, a commutation period does not reach its full value because this is due to the short circuit coil offer a self-inductance in addition to resistance. The rate of change of current, that is because of change in the current, then there is self-inductance of coil sets up a back EMF which is opposing the reversal of current in the coil. The current in the coil, which is I am taking the example of plus IC because current per coil. That is, it is changing from plus IC to minus IC. Then the total change, that is IC minus of minus IC, that is the 2 IC is the total change in the current. The TC is the time of short circuit, that is what we are calling as commutation time, is a time taken to change from plus IC to minus IC. Then the WB is the brush width and WM is the thickness of the mica insulation. Then the VC is the velocity of the commutator segment or a setup of the commutator and the coil which is rotating with the velocity of VC. VC is the velocity of the commutator segment that is missing here. Okay. Now how to find out the time? We know that the basic equation of the velocity is equal to distance by time. Velocity is equal to distance by time. Therefore, time is equal to distance by velocity. That same concept is used here. That is, time is equal to distance by velocity. That is what you mean by the distance moved. That is, the distance moved is nothing but moving from the commutator segment B to commutator segment A. That is the total distance moved here is nothing but it is a width of the brush. That is the total distance traveled. That is, for a commutation process, the distance traveled is the brush from the commutator segment B to commutator segment A. That is the total distance traveled is it is a width of the brush. It is a total width of the brush. And there is small portion of the the mica insulation. Therefore, if you are deducting mica insulation, that what you are getting here is the distance traveled by the commutator or in turn it is a commutator segment. Therefore, the distance traveled here is WB minus WM. That is, you are deducting a mica insulation to total width, a small portion. Okay. Therefore, it is a WB minus WM is a distance moved. The VC is the velocity of the commutator segment. Therefore, distance by the velocity gives the time. Then the reactance voltage is given by L di by dt. That is, what is the change in the current? Change in the current is 2 IC. The L is as it is. The change in current is 2 IC. And the time taken is TC. Then you have to substitute the value of TC in this equation. Then what I am getting here is 2L ICVC divided by WB by WM volts is the reactance voltage. This is the expression for if the commutation is linear one. If the commutation is sinusoidal, then you have to multiply form factor of 1.11 to this equation, so that what I am getting is 2.22 L ICVC by WB by minus WM volts is for sinusoidal voltage. Because of this reactance voltage is inducing, that is opposing the changeover of the current from plus IC to minus IC fully. So that we have to nullify this reactance voltage by the what do you mean by the EMF commutation. For EMF commutation, what exactly we are doing here is we are placing a small poles in between the main poles. That is, I am showing here. Okay, you can see here we are placing the COM poles, or it is also called as a commutating poles, between the main poles, so that they are producing the flux or voltage, they are inducing extra voltage such that is opposing to the reactance voltage. These are connected in series with this commutating windings are connected in series with the armature. Therefore, these are made up of thick wires. Okay, that is, these are the small poles which are introduced between the main poles so that they are nullifying the reactance voltage. These are called as the commutating the poles. Okay. Now we have got a reactance voltage, that is EMF1. This is a, in this method the arrangement is made to neutralize the reactance voltage by producing a reversing EMF in the short circuited coil under commutation. This reversing EMF is, as the name shows, that EMF in opposition to the reactance voltage. The reversing EMF may be produced by in two different ways. One is shifting of the magnetic neutral axis. The another one is by using the interpose. This is the usually they are adopting in the DC machine. That is, they are introducing a small poles in between the main poles so that they are nullifying the interpose. That what we are calling is uh, the interpose. That is what we are calling is EMF commutation. That is, these are the small poles fixed to the yoke and space in between the main poles. They are wound with the comparatively heavy copper wires so that they are connected in series. The function of the interpole is that their polarity is the same as that of the main poles in the case of generator. It is the reverse in the case of the motor, so that their object is to produce the flux or voltage in opposite to the reactance voltage. Okay, this is how we have to write how we are making the commutation the ideal. Okay, there is one numerical we have to solve on this as it is a 4-pole machine, lamp connected with 1500 RPM. It is running with a delivering current of 150 amperes with 64 commutator segments. The brush span is given in terms of, not in terms of meter, it is given in terms of the segment, that is 1.2 times 1.2 segments is the width of the commutator segment. Therefore, and the inductance is 0.05 millihenries. What is asked is to calculate the linear commutation voltage and sinusoidal commutation the reactance voltage. Neglect the mica insulation, that is Wm is taking as a 0. Just you have to list out the data given. Here I am listing out the data here. Wb is 1.2 segment, Wm is 0, Vc is, it is for one revolution, the total number of revolution in 1 second is 1500 by 60, because it is rotating with 1500 rpm it is making, that is 1500 revolution it is making in the 60 second. Therefore, for one revolution it is constituting 64 commutator segment. Therefore, the velocity is 1600 segments per second. Then IC, it is a lap connected winding. Therefore, current per coil is 150 divided by 4, that is 37.5 amperes. Then we have got a commutation time TC, that is a WB minus WM, VC, everything is calculated here. Just you have to substitute, then what we are getting is 7.5 into 10 raised to minus 4. Directly you can substitute, that is or you can substitute in the reactance voltage formula. Then IC is known, VC is known, WM is given, WM is 0. If you are substituting, what you are getting is the reactance voltage is 5 volts. It is for linear commutation. For the sinusoidal commutation, you have to multiply 1.11 to 5. That is what we are getting is 5.5 volts. This is how you have to calculate the reactance voltage for linear commutation and sinusoidal commutation.